if we can get through that. So D says, let dy dx equal this, and we know that h of 1 equals 2, and this is the derivative of the function h, because y equals h of x. When I see it like this, I automatically think I'm going to have to tag any y's. So I have what here is a product rule. So it says, let's find the second derivative and say what that tells us about the concavity. So I'm going to do product rule, so I'm going to take the derivative of this. So the derivative of this will be f prime of 2x, f double prime of 2x times the derivative of the inside, which is a 2. So that's derivative of the first times the second plus the first times the derivative of the second. The derivative of the second is going to be 3 dy dx. Okay, so if I simplify this real quick, I get 2 f double prime of 2x times 3y minus 1 plus f prime of 2x times 3, and then dy dx is equal to that thing up there. So I'm just going to replace dy dx with f prime of 2x times 3y minus 1. Now we're interested in this at this place. This h of 1 equals 2. So every x is going to become a 1, and every y is going to become a 2. So this is going to be 2f prime of 2. If I put a 2 in for y here, this is going to be a 5 plus, again, f prime of 2 times 3 times f prime of 2 times 5. Okay, so f double prime of 2, if I go look at this picture, f double prime is the slope here. The slope is 0 there. It tells me down here in the description. So this part becomes 0. F prime of 2 is equal to 5 times 3 times 5 times 5. So I get what, 375? And again, you are allowed a calculator. So since that's 375, since that's positive, I'm not going to write it out. I did on the other one, but you would say that the h of x is concave up at the point 1 comma 2, since the second derivative is positive. E says, consider the function here. On what intervals is the function increasing? Okay, so it's going to be increasing. So h increases when this function here, its derivative, f prime 2x times 3y minus 1, is greater than 0. They've told us in the premise of the problem, right here in D, that y is greater than 1/3. Well, if y is greater than 1/3, that means this part is always positive. So we are just trying to figure out when f prime of 2x is positive. So f of x is positive from 0 to 4. So if I plug a 0 into here, I get out a 0. But if I plug a 2 into here, I get out a 4. So since it's a 2x instead of an x, I'll say 0 to 2. And then it's positive again from 6 to 9, which all go from 3 to 4.5. Again, because this is not f prime of x, it's f prime of 2x. So I'm trying to figure out how do I get a 6 coming into here and how do I get a 9. And then again from 9 to 10, f prime's positive. So f prime of 2x will be positive from 4.5 to 5. Okay. Then f says, here's this differential equation. So we have dy dx equals f prime of 2x times 3y minus 1. It says use separation of variables. So I'm going to bring the 3y minus 1 over here. I'm going to leave the f prime of 2x here and put the dx over there, and then I'm going to integrate. Okay, so this is a natural log of 3y minus 1. But if I were to take this derivative, there'd be a 3 in the chain rule, which I don't want, so I'm going to put a 1/3 here. Okay, and then the antiderivative of an f prime of 2x would obviously be an f of 2x. But this would also have a chain rule of 2, so I will put a 1/2 in front here. And then I'll put a plus c. Now, you will see that on this problem it says find the general solution. So since it's not the specific solution, it's the general one. We're not worried about finding c, so I'm just going to solve for this, which is the form they told me. So I'm going to multiply both sides by 3. And we get natural log of the absolute value of 3 minus y minus 1 equals 3/2 f of 2x plus c. And that's all the farther I have to go to get it in the form they want. Okay, and that's it for number 1. So I'll be back for number 2 here in a bit.